Hello everyone, and welcome back. Today we're going to continue our exploration of multivariate statistical analysis and focus on how to test if there is a significant difference between two multivariate population mean vectors. Before we get into that though, let's just review some of the basics that we talked about last time. So last time, one of the problems that we were interested in testing was the claim that mu was equal to mu 0, with the two-tailed alternative that mu was not equal to mu 0. Here, mu and mu 0 are both multivariate vectors, in particular belonging to Rk, where k represents the number of features in each of those vectors. Obviously, mu is a parameter vector, and mu 0 is a claim vector associated with that particular population mean vector. So, what did we do? So our primary interest was to collect a multivariate vector from that multivariate normal distribution for which mu is associated to. That vector has the structure x1, x2 down to xk, and if we do n of these multivariate vectors from that population whose mean is mu, right? So x is associated to a multivariate normal whose mean is mu and covariance matrix is sigma, and we typically don't know what mu and sigma are. But if we do n of these, then what we can do is we can construct a sample mean vector x bar, which is going to be of the structure x bar 1, x bar 2, all the way down to x bar k. And this x bar k is going to be a point estimate for that mean vector mu, because we know that the expected value of this sample mean vector is the population mean vector mu. So one thing that we definitely need to understand is that this x does have a variance associated to it, and that variance is equal to sigma, which we approximate with our sample covariance matrix, sigma hat. So obviously for each of these null hypotheses, because this null hypothesis can be represented as mu1, mu2 down to mu k, is equal to mu1, mu2 down to mu k, all of which are the claim values for each of those parameters, we can have a different alpha value associated to each of them. For example, we can have an alpha vector, let's call it alpha, which is going to be alpha 1, alpha 2, down to alpha k, if we want to do element-wise comparisons for each of those. But obviously, you can run into a lot of issues, because if one of these hypothesis tests is wrong, then the whole entire thing sort of falls apart. So what we did was we pooled these alphas into what we call a family-wide alpha value, and from the Bonferroni inequality for probabilities, one should know that that's going to be less than or equal to 1 minus the product from j is equal to 1 to k of 1 minus alpha j's. Right, and we do not necessarily know the exact value of our family-wide, but we can choose to be this upper bound given to be this thing on the right-hand side. So once we choose our family-wide alpha value, then we have a couple of test statistics to work with. In particular, the first test statistic that we introduced was the t-squared test statistic, which was given to be of the form x bar, where x bar is a vector, mu 0, which is the claim vector that we're testing against, transpose, times the inverse of our sample covariance matrix divided by our multivariate sample size, the inverse of that matrix, times x bar minus mu 0. And under reasonable but not practical assumptions, this will be associated to a chi-squared k distribution, but obviously if your sample size is small and our covariance matrix for our sample is not close to the true covariance matrix, it's not going to really be connected to a chi-square distribution. So an often alternative that is used is what is called the multivariate f-test statistic, which is of the form n minus k divided by k times n minus 1. Again, n is the number of multivariate samples you collected, k is the number of features in each of those multivariate samples, times that t-squared test statistic that is mentioned above, and this will be associated to an fk n minus k distribution, provided that our covariance matrix is not super different than sigma, and our sample size n is arbitrarily large, and x comes from a multivariate normal distribution. So those are the things that we definitely should know up to this point. Now we're going to consider our new problem. So now consider comparing two population mean vectors. So two population mean vectors. So what exactly does this look like? So we're going to have one population, call it P1, another population, call it P2. So this population 1 has a mean vector mu1, and then sigma 1, and over here we're going to have mu2, and then we're going to have, for example, sigma 2. Now let's assume we're interested in testing the null hypothesis that mu1 is equal to mu2, with a two-tailed alternative that mu1 does not equal to mu2, and here mu1 and mu2 both are associated to having the same k features in the same exact order in each of their corresponding vectors. And let's also assume that P1 is associated to a multivariate normal distribution with that mean and that covariance matrix, and P2 also is associated to a multivariate normal distribution with some mean mu2 and covariance matrix sigma 2. Right? So that's the problem that we're going to be working here. So the very first case, so case 1, that we're going to be concerned with is going to be sort of following the parallel like we did with the univariate case, and that is P1 is dependent on P2, or P2 is dependent on P1. So what exactly does that mean? So that means that there exists a meaningful one-to-one correspondence between P1 and P2. The most common example for this one-to-one correspondence is usually associated to before and after studies. So if you have a before and after study that you're interested in testing, then this case 1 test for multivariate vectors probably is going to be the thing for you. So what are we going to do? So we're going to gather a multivariate sample from population 1, let's call that sample S1, and we're going to be collecting a multivariate sample S2 from P2. And the restriction on these sets is that the size of S1 and the size of S2 are both going to be equal to n, and each of these x's in these sets are not just values but vectors, and those vectors are going to have k features each, and k obviously should be bigger than or equal to 1. So for example, we're going to collect n individuals, and for each of those individuals we're going to have a response associated to several questions for each individual. So let's actually take a look at what that looks like in terms of its underlying structure. So what is our null hypothesis? So, in general, in vectorized form, that's mu1 is equal to mu2. If we expand that out by looking at each of the features, we have mu population 1 first feature, mu population 1 second feature, all the way down to mu population 1 the kth feature, and that's going to be equal to mu second population first feature, mu second population second feature, all the way down to mu population 2 last feature. Right? So what exactly are going to be our samples that we're going to collect? So our first sample is going to look like x111, x112, x113, all the way down to x11m. Right? So this is the first population, first question, first response. So this is going to be the first population, first question, second response, or second individual. This is going to be the first population, first question, third individual's response, and then this is the first population, first question, the last response for that question. And then we're going to have the same for the second question. So we're going from the first population. So x121, x122, x123, all the way down to x12m. And that's going to continue all the way down to x1k1. So that's the first population, last question for my first individual. And then we have x1k2, so that's my first population, last question, second person. And then we're going to have x1k3, so first population, last question, third response. And then that's going to continue all the way down to x1kn, so first population, last question, last response. So this is going to be a matrix. And from this particular row, we're going to be able to calculate an x bar 1, 1. From this bar row, we're going to be able to calculate an x bar 1, 2. And from this last row, we're going to be able to calculate an x bar 1k. So it's going to be a bunch of sample means for each feature, which is going to be serving as an approximation for mu11, mu12, all the way down to mu1k, which is the very first vector. And then we're going to be doing the same for the second sample. So the second sample is going to be of a similar structure, so it's going to be x211, x212, x213, all the way down to x21n. So the first entry is going to be equal to the second population, first question, first person, second population, first question, second person, all the way down to the second population, first question, last person. And then we're going to have x221, x222, x223, all the way down to x22m. And that's going to continue all the way down to x2k1, x2k2, x2k3, all the way down to x2kn. Right, so that's going to be our structure for our second matrix, right? And let's just make sure we understand that. So this individual here is from our second population, the last question, and the third individual's response for that particular question. So similarly to before, we have this row is going to calculate an x bar 21, and then an x bar 22, all the way down to x bar 2k. So we're going to have a sample mean for each feature for the second population, and this is going to serve as a point estimate for mu21, mu22, all the way down to mu2k. Right? Now, for case 1, we're associating a meaningful one-to-one correspondence. Therefore, this person here is actually the same person there, but at a different time. So, for example, that could be, for example, your age before and your age after for the same person. So this is your age before and age after for the second person, and then this last element is going to be your age before, age after for the last person. Similar, this is going to be, for example, your height before and your height after for the same person. And then over here we have, for example, the height for the second person before, the height for the second person after, all the way down to the last person's height before and after. And then down here, for example, we have, I don't know, your happiness value for the first person before and your happiness value for the first person after, all the way down to the happiness of your last person before and the happiness of your last person after. So those circled with the same color are associated to the same person, just at different time, right? So we can, I guess, summarize this as per person. So for each person, 1 to n, we ask a same question, in particular, k of them, at 2 different times, right? So this is associated to the sample size, this is known as the number of features, and this is known as the number of groups or populations that are being investigated in this particular test. So since we are associating a meaningful one-to-one correspondence between these two samples, then we should be able to construct a sample of differences between these two samples. So let's call this sample SD. So SD is going to be of the form XD11, XD12, let's call it XD13, XD13, all the way down to XD1M. And then XD21, XD22, XD23, all the way down to XD2M, and that's going to continue all the way down to XDK1, XDK2, XDK3, all the way down to XDKN. Right, so this is just going to be a multivariate sample of size n for each of these differences. Right? So let's just quickly define what each of those elements represent and how to calculate them. So xdji will be equal to x1ji minus x2ji. So if we go back up to our matrix, we're going to be taking this element minus that element minus that element, this element minus that element, and this element minus that element in that order. And you should be doing it in the same exact direction for all. So you could either do sample 1 minus sample 2 or sample 2 minus sample 1. It's really up to you. Just stay consistent. Right, and this is obviously with j is equal to 1, 2 down to k, the number of features, and I is equal to 1, 2 down to n for each individual sample. Right, so this first row is going to give us an x bar d1, so an average of those differences. Then from here we're going to have an x bar d2 all the way down to an x bar dk. Right, and that's going to give us a vector, and this is going to help us approximate the population mean difference vector mu d1, mu d2, all the way down to mu dk. So once we have that particular point estimate for that particular vector, then we can restructure our original null hypothesis. Right, so what we're going to do is we're going to define x bar d to be equal to those difference means. So x d1, x bar d2, all the way down to x bar dk. And let's assume we define mu d to be equal to mu d1, mu d2, all the way down to mu dk. So here our null hypothesis that we started with was mu1 is equal to mu2, and this is now going to be translated into h0 is equal to mu d is equal to the 0 vector, where a point estimate, and this is actually very easy to prove, is that the expected value of the sample mean difference vector is actually equal to the population mean difference vector. So quite a nice proof for you to verify. All right, so once we have that, let me just make a quick note. Our sample matrix represents xd, which is x1 minus x2, where xd is just going to be a bunch of difference values, xd1, xd2, all the way down to xdk, right? With xdj is equal to x1j minus x2j. So those are the random variable representations for our samples, where j obviously ranges from 1 to k. So if you have this particular vector, which we already know how to estimate, because we have a sample for that, we have a sample for that, we have a sample for that, so we have a bunch of values for that, this bunch of differences is going to have an associated variance for that. And we're going to be representing that by the covariance matrix for the differences, for which we can easily approximate as the covariance, the sample covariance for our differences. Now, it's very important to note that if the variance of our first vector is sigma 1, and the variance for x2 is, say, sigma 2, then the covariance matrix for the difference is not equal to the difference of covariance matrices. This follows parallel, just as before. So this is the covariance matrix for the differences. All n times k of them. Right? So once we have that, then we should be able to build some nice test statistics for that. Right? So our null hypothesis, again, is that mu d is equal to 0. Here 0 is a vector. So let's just clarify that just to be sure. So our t squared test statistic is going to be equal to, so we're comparing the point estimate for mu d, which is x bar d, to the claim value of mu d, which is going to be equal to the 0 vector. We're going to be transposing that. Then we have our covariance matrix here, which is going to be our covariance of differences. We have n pairs of them. Invert that, and then we have x bar d minus 0, and obviously that's going to be associated to a chi-squared k distribution if everything is wonderful. And keep in mind, this is practically just the Mahalanobis distance with respect to the difference distribution, because if x1 is multivariate normal and x2 is multivariate normal, the differences also should follow a multivariate normal, so this still is a Mahalanobis distance representation. But most people do not use a t-squared test statistic because the approximation for sigma hat d usually is very, very off from the true value. So an f-stat is typically a little bit more appropriate, and the numerator and the bottom is the same, just like the comparing a vector of means to a constant vector, where we take that and multiply that by our Hotelian t-squared test statistic, which will, as usual, follow an fk and minus k distribution, right? And let's just reiterate what each of these stands for, where n is the number of multivariate pairs, and k is the number of features in each pair, right? And we're assuming that we're only focusing on two groups here. So that is how to take care of the dependent case between two multivariate populations. Now let us consider the case where the samples and the populations are independent of one another. So how are we going to handle the independent multivariate populations case? So this is going to sort of be analogous to the pooled variance and unpooled variance t-test that we discussed back in the univariate world. So obviously the null and alternative hypotheses are not going to change because we still have mu1 is equal to mu2 with the two-tailed alternative that mu1 is not equal to mu2. Where each of these means are vectors with k features. So obviously we're not going to be subtracting them because that doesn't have any meaningful connection to these populations because they're independent. So we need to treat them as just separate entities. So obviously we have one multivariate vector x1, a second multivariate vector x2, for which each has their own covariance matrix, say sigma 1 and sigma 2. And we're obviously going to be approximating each of them with sigma hat 1 and sigma hat 2. And we can't really pull them together in the difference sense anyway, because we don't necessarily know that they're connected. Now, if we have our x1 and x2 and we collect n of them, then we should be able to calculate a vector x bar 1 and x bar 2, which are both obviously k-feature vectors, where x bar 1 is going to be an approximate for mu1 and x bar 2 is going to be approximate for mu2. So let's break down these cases, case 2, and case 3. So case 2 is going to be the case where we have evidence to believe that sigma 1 is equal to sigma 2, or we see, at least from the statistical sense, that the covariance matrix 1 and the covariance matrix 2 are approximately equal to each other. And if we know that sigma 1 and sigma 2 are not equal to each other, or we have statistical evidence to believe that sigma 1 hat and sigma hat 2 are super far from each other, in order to provide evidence that the true covariance matrices are not equal to each other, that's going to break up these cases. So the case 2 is what is called the pooled covariance matrix test, and this is going to be referred to as the unpooled covariance matrix test. And we're going to be assuming that both P1 and P2 are multivariate normal. If we break that, obviously you need to go into, say, a non-parametric multivariate test, which we won't get into here. Right? So let us first dive into the case 2 because that's probably super familiar to you by now. So for the null hypothesis that mu1 is equal to mu2, and we can technically extend this all the way down to, say, mu g, where each of these are k multivariate vectors, and this is obviously a multivariate extension for the ANOVA case. Some people will refer to this as a multivariate ANOVA test. We can build the pooled covariance matrix similar to how we did for the univariate case. So the pooled covariance matrix, which we're going to notice this, so this is the pooled covariance matrix, is going to be equal to sort of like a weighted average of our covariance matrices for each of our populations. So this is going to be nu1 sigma hat 1 plus nu2 sigma hat 2 all the way down to nu g sigma hat g, all divided by nu1 plus nu2 all the way down to nu g. right? And here are degrees of freedom, nu j, is just going to be the sample size from those populations that we were able to gather, minus 1, right? So it's the size of your multivariate sample. Let's actually just write that. So n is the size of your multivariate sample from population j, right? But for our particular test, we don't have G populations, and in particular, in our case, we have that G is equal to 2. So our pooled covariance matrix is just going to be equal to nu1 sigma hat 1 plus nu2 sigma hat 2 divided by nu1 plus nu2. So that's our 2 population pooled variance test. Right. So obviously what we need to do is we need to build a variance for the difference in these sample mean vectors, which we can of course equivalently write as variance of x bar d, because we're using x bar d as an approximation for mu d and seeing if it's close to 0 or not. So one can prove that this is actually equal to sigma 1 divided by m1 plus sigma 2 divided by n2, provided that these two things are independent from each other, where population 1 and population 2 have covariance matrices, sigma 1 and sigma 2, and those n1s and n2s, again, are the size of your multivariate samples from population 1 and 2, respectively. Right? So this is where the story, of course, changes depending on the pooled versus unpooled variance t-test. So if we have evidence to believe that sigma 1 and sigma 2 are equal to each other, then we have the variance of x bar d, because we can just call them equal to, say, sigma, right? So we can say that this is going to be equal to sigma over m1 plus sigma over n2, which is just going to be equal to sigma times the constant 1 over m1 plus 1 over n2. Therefore, instead of approximating sigma 1 and sigma 2, we're actually just approximating sigma. So what's a good reasonable approximation for sigma? Since we know they're equal to each other, both sigma hat 1 and sigma hat 2 are good choices. So we can approximate this with the pooled covariance matrix times 1 over m1 plus 1 over n2. And I'm going to give this a name. I'm going to call this sigma hat differences and then P for pooled. So this is the covariance matrix for the differences, because that's what we're focused on, for the pooled variance or pooled covariance t-test. And if we have evidence to believe that they're not equal to each other, so if sigma 1 is not equal to sigma 2, or the sample covariance matrices are far from each other if we don't know the former, then the variance of x bar d is just going to be approximated by sigma hat 1 plus sigma hat 2, all divided by their corresponding sample sizes. And I'm just going to be calling this matrix sigma hat for the differences, but for the unpooled case, right? Let's actually put that in a different colored box, right? So we have the covariance matrix for the differences for the pooled and the covariance matrix difference for the unpooled variance t-test. So from there, the rest is practically the same as the paired difference t-test in the single mean test. So our t-squared test statistic is just going to be equal to x bar 1 minus x bar 2, where those are your sample mean vectors transpose, times the covariance matrix, let's just subscript that with d, inverse, and then that's going to be x bar 1 minus x bar 2, which is as usual going to follow a chi-squared k distribution under reasonable conditions. And obviously, this could be either sigma hat dp or sigma hat dup, depending on which case you're sort of falling in. And once you have your t-squared test statistic, you can build your associated f test statistic, which is going to be equal to n1 plus n2 minus k minus 1, all divided by k times n1 plus n2 minus 2. And that's going to be multiplied by our t-squared test statistic from above, and that's going to be associated to an f k nu p or an f k nu up, right? So this is your pooled and this is your unpooled, right? So the degrees of freedom obviously is going to be different depending on the test that you are in. And That should be familiar from the univariate world. So the pooled variance degrees of freedom is actually quite nice. So the degrees of freedom for the pooled covariance t-test, right, is going to be equal to n1 plus n2 minus k minus 1. Again, n1, n2 are sample sizes from our multivariate populations. K is the number of features. And the unpooled is actually quite beautiful, at least theoretically, but on top is going to be equal to your t-squared test statistic for your unpooled to the power of 2. And on the bottom, we're going to have the sum from j is equal to 1 to 2, because we have two populations, 1 over nj squared times our degrees of freedom. So that's the same as before for our univariate case, times x bar 1 minus x bar 2 transpose, and then we're going to have the inverse of your unpooled covariance matrix for the differences times the covariance matrix for the population under interest, because we're going to be summing up two things, 1 and 2, and then we're going to have the covariance matrix for the difference, unpooled, invert that, and then we're going to have x bar 1 minus x bar 2, close bracket, squared, right? So you're going to have, if we sort of expand this, if this formula confuses you, you're going to have t squared stat, the quantity squared, all over 1 minus nj squared nu j times matrix stuff for 1. Let's actually change those subscripts since we're sort of breaking it down here. So that's going to be n1 nu 1, and then we're going to have 1 over n2 squared nu 2 times matrix for stuff 2, and those matrix things are squared. So that's going to be your degrees of freedom, and you can always check and see if that makes sense, because it should be near n1, n2, the average, slightly above or slightly below the min and max respectively. Right. So once you have your test statistics, either T or F, whichever you think is appropriate, then you usually interpret it in the same exact way. So for example, if your test statistic is greater than your F critical value, and that F critical value is obviously going to be built with a conservative alpha family wide, since we're doing everything vectorized, we don't need to split that. Then we're going to be rejecting the null hypothesis that mu1 is equal to mu2, which means that our vector x bar 1 and x bar 2 are significantly different from one another. Right? But obviously you could have a type 1 and type 2 error as usual, but that's how you would go about it in the pooled and unpooled covariance matrix world. And keep in mind, these assumptions are heavily reliant on the fact that both x1 and x2 are multivariate normal random vectors. So there's one question that remains in order to complete this particular story, and that's how to test whether or not our sample covariance matrices are close enough in order to imply that the true covariance matrices are close enough too, right? So let's just go back in the day and recall the univariate test, which is sometimes referred to as the Bartlett test for equality of variances. And then null hypothesis was of the form sigma 1 squared is equal to sigma 2 squared is equal to all the way down to sigma g squared, where g is the number of populations under consideration. So obviously there are a few other variations, such as the Levine, the Brown-Ford-Scythe, the squared ranks test that you probably should know, but we're just going to be using the Bartlett test so that we at least have one test to work with. So the Bartlett test statistic is given by mu times the natural log of the pooled variance for our populations minus, and let's just put that in bracket, and then minus the sum from j is equal to 1 to g of our individual degrees of freedom times the natural log of our individual variances all over 1 over 1 plus 1 over 3, and then g minus 1. And then in this bracket, we have 1 over nu 1 plus 1 over nu 2, all the way down to 1 over nu g minus 1 over nu. And this is going to be associated to a chi-squared g minus 1 distribution as long as your sample sizes are relatively large, and each of these populations are associated to a normal distribution. A couple clarifications on terms of notation. Nu is equal to nu1 plus nu2, all the way down to nu g, and nu j is just going to be equal to nj minus 1, because we do not mandate that the samples need to be the same exact size. Right? So that is your Bartlett test statistic, and that'll give you sufficient evidence to believe that all of the variances are equal. Right? So what exactly does the Bartlett test do? So it does for multiple populations, in particular G of them, for univariate samples of size nj, right? And when I say univariate, I mean k is equal to 1. So if we want to increase this into the multivariate world, which we definitely need, then we need to be able to generalize this to an arbitrary k, like k is equal to 2, k is equal to 3, k is equal to 52. Anything is good, right? So a multivariate extension of the Bartlett test is what is referred to as the box test. Some people will call it the box M test, but I'll just call it the box test for now. Right? So the BO stat, the box test statistic, is going to follow a similar structure to that of the Bartlett test statistic. So it's going to be equal to the degrees of freedom times the natural log of the determinant of the pooled covariance matrix. So that's the same pooled covariance matrix from the pooled covariance matrix t-test. And then minus, let's put a double bracket around that just to be safe. So the sum from j is equal to 1 to g of nu j times the natural log of the determinant of the covariance matrix. Actually, I can put the brackets inside of the sum. We know what we're doing here. Right, so what are we doing here? So remember, before it used to be sp squared and sj squared, which is the variance. But here we're looking at the determinant of the covariance matrix. And the determinant of the covariance matrix. Remember what the determinant of the covariance matrix is. So the determinant of the covariance matrix J, that's actually just the sample generalized variance for xj. Right? So the box test is considering if the generalized variances are significantly different from each other. And you could also do a variation of this and look at the total variance if you want, but generalized variance is usually a little bit more useful because instead of just looking at the diagonal, you should be looking at all of the elements in the covariance matrix, right? So the box test is looking to see if the generalized variance for our multivariate samples is significantly different from each other. All right, and on the bottom, we're going to have 1 minus 2k squared plus 3k minus 1 all over 6 times k plus 1 g minus 1. Let's put that in a little bracket. And then over here we're going to have 1 over nu1, 1 over nu2. This is the same as before. 1 over nu g times 1 minus nu. And then actually I want to put this in a different color because sometimes it's easy to forget. So this needs to be raised to the minus first. So technically it's not on the bottom. It's on the top, right? So it's the top times that bottom thing. And this is going to be associated to a chi-squared degrees of freedom. I'm going to call it nu BO. And nu BO is going to be equal to k times k plus 1 times g plus 1 divided by 2. Obviously, since k is bigger than 1, this test statistic for chi-squared needs to be a lot larger than that from the Bartlett test statistic. Right? So, and keep in mind of the assumptions for both Bartlett and box, that P1, P2, all the way down to PG are all multivariate normal. And if you slightly vary, because you can test multivariate normality via, say, a quantile plot for your squared Mahalanobis distances, per se, for each of them, and make sure they follow practically a normal distribution. If you have any slight deviation from normality, the box test can be very, very misleading, and other more advanced techniques probably need to be taken into account. But those are all of the important things that you definitely need to know when it comes to testing the difference between two multivariate mean vectors, and also how to test the equality of multiple covariance matrices, provided that normality condition is met. Hope you enjoyed this video, and I'll see you in the next one. Take care.